In this video, we are going to learn about method of use substitution in integration. We are not only going to learn about how to apply that method, but we will also learn about when to apply that method because that's extremely important and nobody talks about it. We will also learn about some exceptions in use substitution that nobody has ever talked about ever in the entire YouTube. Let's get started. There are really two situations when we have to do method of substitution in integration. Case number one, which is the most common, is when you have to deal with composite function. I'll tell you in a minute what a composite function is. But the another situation when you have to do method of substitution is when you have a function which is not directly integrable using the standard integration methods that we have. Okay, and these are really some special cases that we deal with. We are going to learn about all those cases in very detail, so you don't have to worry at all. But remember, the functions which are not directly integrable using the standard methods, these are nothing but special cases. Okay, Weierstrass substitution is one of the examples of those special cases. I have attached a video on the top that you can see right now for Weierstrass substitution, but that's one of the special cases. We are going to learn more of those special cases in detail. Okay, now let's move on to composite functions. Composite functions are the functions which are function within a function. Okay, let me give you an example. Let's say I have a function sine. Okay, and then inside of sine, let's say I have cos x. Okay. Now this is an example of composite function. Okay. That's example number one. Example number two is, let's say when you have a square root of sine x, for example, I have a square root which is a function and sine x is another function. So this is function within a function. That's a typical example of a composite function. Okay. If I have to give you another example, it could be log x to the power m. Okay, so to the power m is a function and log x is a function within that function. Okay, so these are all examples of composite functions, and I can give you infinite more examples, but that's, I think you get the idea of what are composite functions. If I want to represent all of those in general terms, they are represented by f of g of x. Okay, where f is the outer function and g is the inside function, and that's the representation of composite function. In most of the situations when you deal with the composite function of the type f of g of x, the method of substitution that you are going to do in order to integrate is put g of x, which is the inside function, is equal to u. Okay, that's the method of substitution that we are talking about. Now, whenever you do method of u substitution, there is one condition that should always satisfy in order for you to be able to do u substitution. Okay, which is that the derivative of that u should always be present in that integral. Okay, what do I mean by that? When you put gx is equal to u, remember the condition says that the derivative should always be present, which means that the derivative of u with respect to x should be present. Okay, whatever u you put, the derivative of u with respect to x should be present in integral, should be present in the integral in the product form. Okay, it should be present in the product form. It shouldn't be present in the denominator. It should be present in the product form. And this is what nobody is going to ever teach you on entire YouTube. Now remember that this condition is true for both of these situations, whether you are dealing with composite function or whether you are dealing with a function which is not directly integrable. Okay, this du by dx should always be present in the product form whenever you are doing that u substitution. That's the rule. Now let's learn about how to apply that method of u substitution. Let's say if you have a function f of g of x and there is g dash of x getting multiplied. Okay, whenever you want to integrate a composite function, remember the method that we do is method of u substitution. And based on what we have studied, we put g of x is equal to u. That's the method of u substitution that we did. Now, after this step, what you do, just differentiate both the sides. Why do we differentiate both the sides? Because now we have to convert this integral from the x world to the u world. So if you want to convert this integral from the x world to u world, we'll also convert that dx in terms of du. So if you want du over here, or you want to find the value of du, you will have to differentiate both the sides with respect to x. So differentiate both the sides with respect to x. Derivative of g of x with respect to x is g dash of x. Okay, derivative of u with respect to x is du by dx. Okay, now what you do, notice that if you want to convert this integral in the u world as we discussed, you need d of x and there is a g dash x getting multiplied over here. So if you notice these two terms, g dash of x times dx, that you see getting Now, if you notice this integral carefully, that g dash of x times dx is getting generated over here. If you just multiply by dx on both the sides, or just take that dx over here. So what you get is g dash of x times dx is equal to du. So what you are able to generate from here is these two terms combined can be written as du. So now you are able to convert that dx in terms of du. Okay, so we can now convert that integral in the u world and say this is integral of f of gx is nothing but u. So I can just say this is fu, and these two combined is nothing but du. So you now converted that integral from the x world into the u world right here. Now let's discuss about a quick exception that we deal with in method of u substitution. We do it frequently, but no one ever talks about it. That exception is whenever we want to put gx is equal to u. Remember, in most of the general cases, we want a derivative of g of x or derivative of u present in the product form in order to be able to put gx is equal to u. That just makes our converting to the u world whole lot simpler. But there are situations when the derivative of that g of x, which is g dash of x, is not present in the product form. Whenever that happens, that your derivative of u, which is du by dx or g dash of x, is not present in the product form, you can still do method of u substitution. But yeah, what you have to do is instead of having gx is equal to u, so just put gx is equal to u anyway, and then instead of taking derivative directly that we normally do, find the inverse of that function. So find the inverse, which is g inverse of u is equal to x. Let's understand this with the help of simple example. Okay, let's see if I put in an integral, if I have to put u is equal to tan theta. Now we know derivative of tan theta is sec square theta. Let's say there is a situation where sec square theta is not present in that integral. So what you do, instead of trying to arrange the derivative, just take the inverse of this function. So this is u in terms of theta. You just take an inverse of this. Okay, so this will become theta is equal to tan inverse of u. That is what I mean by take g inverse of u is equal to x. Convert it from u is equal to function of x to x is equal to function of u form by taking an inverse of that function, and then proceed to take derivative. So now you can take derivative with respect to u and say d theta by du is equal to 1 upon 1 plus u square. The best example of this method is the Weierstrass substitution. In order to learn more about Weierstrass substitution, you can check the link on the top attached right now. I think that's a lot of theory. I think it will be best if we can look at some examples right now and see how we can nail those examples by using these techniques. Now let's look at this example. This is a composite function example where you have an exponential function, and within that exponential function you have an inverse function. Okay, so this is of the type f of g of x. Okay, notice that the derivative of tan inverse of x, we know that if tan inverse of x is a function, derivative of that tan inverse of x is nothing but 1 over 1 plus x square. Okay, so if you notice that the derivative of the tan inverse of x is present right here. Okay, if the derivative of tan inverse of x is present, what we can do in order to integrate this is put tan inverse of x is equal to u. The moment you put tan inverse of x is equal to u, now our goal is to convert this integral from the x world to the u world. In order to convert this integral to the u world, we have to convert that dx in terms of du. If you want to convert that dx in terms of du, we need to find du from here. So in order to do that, differentiate both the sides with respect to x. So derivative of tan inverse of x with respect to x is 1 over 1 plus x square. Derivative of u with respect to x is du by dx. Now, if you observe this integral carefully, you have dx over 1 plus x square over here, and that is also getting generated over here. So if you just multiply that dx in on the left hand side, what you have is just multiply that dx over here. So you have dx over 1 plus x square is equal to du. Okay, that's what we were able to generate from that derivative function, derivative equation. So you can now convert this entire integral in the u world, and you will say e to the power tan inverse of x is nothing but u. So you say e to the power u, and this dx over 1 plus x squared, dx over 1 plus x squared is nothing but du. Now integral of e to the power u with respect to u, we know is nothing but e to the power u. And in integral, we add the constant of integration, arbitrary constant c. Now e to the power you just resubstitute and convert it back to the x world. So this will become e to the power tan inverse of x plus c, and that is your final result. If you understand the concepts that I'm teaching you, can I request you to like this video and subscribe to this channel? You will not find such valuable content anywhere on YouTube. I do post calculus and math content every single day. That's another reason to subscribe. I'll see you tomorrow.